Welcome back to the next section. We're going to continue with the actual PLC code that we're going to encapsulate in the add-on instruction. Okay, let's talk about code for a minute. Remember that this add-on instruction is going to provide us with diagnostics at a level that would not ordinarily be part of a machine build. So we ask ourselves, we want to know if a cylinder is slow in extending or not extending within the elapsed time documented at the time the process was commissioned. So in other words, we're going to add logic that is going to be tuned to each cylinder in the process. When we commission the machine or the process, we set the flow controls on the pneumatics, and then we look at the extend and retract time, and then we set up our diagnostics based on that. So we want to know if the cylinder is slow in extending. In other words, if the situation is deteriorating, if the process is deteriorating mechanically, or even if a space cadet has walked by and adjusted some of the flow controls. Or if it's not extending within the elapsed time, then we want to declare a fault. So going beyond the traditional logic that energizes or de-energizes the solenoids on the valve manifold, there is an entire realm of diagnostics that you can supply to the machine operator and maintenance people if you add the logic to do so. And you're going to do this to monitor the time intervals between the command and the completion of cylinder motion. So from the time that you energize the output to extend or retract the cylinder until it's actually sensed by the end of stroke sensors that it's been completed. Now, most projects do not budget for these features, so they seldom get implemented unless the end user does so after the fact, and you know that seldom occurs because everybody's busy. So if you can add these diagnostics at little cost, your machine has an edge on the competition. Although it is not a component of this presentation, there are also faceplates that you can create for add-on instructions, and they will back the add-on instructions. So you can actually have little graphics that are pre-made that go along with each one of these instructions. Faceplates, like add-on instructions, are classes of visual objects that can be added to your HMI screen as an instance, and they are animated with the data from your instances of the add-on instructions. This is the basic logic to monitor the interval between command and completion of the extend and retract cylinder and declare a fault if it is excessive. Of course, the timer presets are determined at the time of commissioning of the machine and are unique to each cylinder on the machine. If the extend motion interval exceeds the preset of the timer instruction, a bit is set or latched to capture the event, both the extend motion and the retract. As you know, flow controls are adjusted to maximize the speed of the process without allowing excessive banging at the end of stroke. If the operator or some space cadet walking by plays with the flow controls, this logic will detect that variance and announce it through the logic. For the sake of good logic grammar, we modify the logic to make it more conventional, but it still functions the same. So you see, the only thing we did was because the done bit will not be on if the timer's not timed out, then we can actually collapse it up into around the TON instruction. Because if we don't have a cylinder extend solenoid energized, the timer won't be enabled and it'll be cleared back to 0 and the done bit set back to 0 anyway. So we just modify the logic a little bit to meet good reading. What else can we add to our diagnostics? While we are considering this one challenge, why not capture the actual elapsed time interval between when the bit memory was set to energize the solenoid valve and the bit in memory was set declaring that the piston had arrived at the extended switch on the cylinder. If you look closer, you will see a problem with this logic. Now this is the solution. We need to capture the timer's data type's accumulated register value at the instant that the end of stroke is sensed by the sensor at the extended end of the cylinder. If you look close, you'll see a problem with this logic. Our tendency is to add logic in the sequence that we think of it. In other words, in the sequence that it occurs. And that's what we did here. In other words, we had a timer that times out and latches an extend fault. And then we thought, oh, let's capture the actual accumulate value where the cylinder extend switch actually was made. And we do that with a one shot because we only want to move one value into that register or tag called extend ET. However, there's a problem with this code. It is scan dependent, and this will defeat the new logic. Ladder logic diagrams scan from left to right and top to bottom. In order to capture the ET at the instant the cylinder extend switch is energized, the logic must copy the accumulate value from the timer data type structure before the timer instruction loses the enable and completes the false execution for that instruction, which is to reset it. So we don't want that timer to reset before we actually capture the ET. If you look at this logic, you'll see if the logic scans from right to left, top down, the first scan where the extend switch is made, the first part of this rung will be false and the TON will reset itself. When it gets down to the third branch, the extend switch is now made and you one shot a move that moves a 0 into the ET. That's not what we want. Looking at the sequence of the scan as it is now, the true if off instruction, cylinder extend switch, that enable the timer will go false and the timer will reset before the lower branch is scanned to capture the accumulate with the move instruction. The accumulate parameter will always be 0 in this sequence. How do we fix this? We move the bottom branch to a position earlier in the logic scan, so it gets scanned first. So we'll back up and do that again. Look at your cylinder extend true if on, one shot, and the move. We just take it and move it up so it's first. Therefore, when the extend switch is made, it one shots the move, moves the accumulate into the extend ET register. Then in the next branch, that's false, so it resets the timer, and so on. So this is called scan-dependent logic. You always have to be aware of this. And I mean, I've actually done this logic many times and forgot, and then it didn't work, and I looked at it and I thought, well, that's strange. I've done it. Oh, and I remember that it's scan-dependent, and you have to move it to an upper part of the rung. Of course, if you create an add-on instruction, you'll never have to look at this logic again. So what else can we do? Well, there's an additional feature that we want to add, an additional challenge that can rise up while you are debugging the logic for a cylinder. This is brought about by the physical nature of a pneumatic cylinder between the end of stroke and the sensors that provide these two events. And if you work with cylinders and sensors, the sensors slide in slots on the side of the cylinder body. And so you basically put the cylinder at one end, slide the sensor until it comes on, tighten it down, and then you do the same thing on the other end. Seldom do you manage to adjust the position of the sensors to respond exactly at the moment that the cylinder reaches the end of its stroke. And this is not a good idea anyway, because a little movement by the sensor and it may not sense the end of stroke. So you place the sensors on the cylinder to sense the arrival of the piston just before the end of stroke. In other words, so the sensor is well made, which means it makes a little early. and then use a timer to delay the event for the logic. Again, we use a timer instruction to create this delay, and the done bit becomes the actual event in place of the sensor that initiates the timer instruction. So if you look at this a little closer, you'll see when the cylinder extend switch is made, it enables a timer, and 200 milliseconds later, that's a fifth of a second, the done bit comes on and turns on the extended bit. So the extended bit is now our sensor, not the extend switch. We have a 200 millisecond delay in there that allows us a little leeway on the adjustment. So let's add this to our existing logic. Let's look at the expected sequence of this logic while it is executing. This logic is dormant until the solenoid is energized. If the solenoid has been energized, and if the extended sensor has not been energized yet, then we enable a timer with the not extended to accumulate increments of time in thousandths of a second. So the instant that we turn on the solenoid, the not extended is true, which starts a timer. So something's going to happen first. Either the timer is going to time out, or the switch will make the end of stroke, which then this timer will reset, and the debounce will start, and then a fifth of a second or 200 milliseconds later, we'll get the extend bit on. And so there's no fault, no warning. Okay, if the timer times out, in other words, if the extend switch isn't made yet and the timer times out, the done bit is set, and when the done bit is set, then it sets the extend fault bit. Now the idea here is we want the extend fault to be set. Now, I show no preset value for cylinder extending TON, but it might be set at 2 seconds, 1500 milliseconds, 2000 milliseconds. It's a length of time that is more than enough for the cylinder to have made full extension. If it's late getting there, in other words, if you set it to 2 seconds, because when you commissioned this machine, it was only 1 1/4 second, so you give it 2 seconds to get there. Even if it gets there a little over 2 seconds, we still want the fault because there is a problem. This way the fault bit stays set. Even if the logic goes false, it still retains that. However, in another scenario where the timer doesn't time out, or the piston rod reaches the end of stroke and the extended sensor energizes, before the timer times out, and that of course enables the debounce timer, and 200 milliseconds later the debounce timer data type times out and sets the done bit, and consequently the extended bit is set. And so we're using the extended bit, not the switch, for capturing time and for the fault. The extended bit is on, and the move instruction copies the value into the extend DT. Now we show 0 in the accumulate, but technically, and we show 0 in the cylinder extending timer on delay instruction. But really that would be set, cylinder extending down there would be set probably at 2000 milliseconds, and maybe we got to 1380, milliseconds, we move that into the extend ET, which means every time we extend that cylinder, we have recorded the time it took for it to extend from the time the solenoid energized until we actually declared it at the end of stroke. And because the extended bit is on, the true if off instruction addressing the extend bit in memory is false, and the TON is no longer enabled. So we're no longer going into a false state. There is more logic to monitor cylinder that you would ordinarily see. This is more logic to monitor cylinder than you would ordinarily see in a conventional program. But there's more. As long as we're monitoring the ET of each stroke, why not create a warning point or a percentage of the fault interval that announces a warning to the operator that a stroke or strokes are deteriorating. To do this, we need a percentage of the preset for a fault. But that preset is adjustable for each cylinder in each application, and we do not want the programmer to have any more variables to adjust than necessary, or rather the operator or the maintenance personnel. So we calculate a percentage of whatever the preset is with using a little math. I always preface this type of math with a greater than zero instruction to skip the logic if there's not going to be any logical result from executing it, and sometimes it avoids math faults, overflows, underflows, etc. So if you look at this, if the accumulate value is greater than 0, and if we actually take and we're multiplying it by 75% or 0.75. So the preset, not the accumulate. So this multiply instruction, it's seldom ever going to change unless you go in and change source B to give it a different percentage, or you change the preset on the timer. So the extend warning elapsed time will be 75% of whatever the preset is. If the accumulate value is greater than or equal to the extend warning ET, then we latch on a bit saying there's a warning. Now, warnings don't normally stop machines, but they do put messages up on the screen to warn the operator that his operation has a slow cylinder. Let's look at the whole run. Okay, let's peruse through this and check it out one more time here. Looks like a lot of code, and we'll actually simplify this here in a minute. So you see it's all predicated on the extend solenoid. So if you look at the top to the left, cylinder extend solenoid. From the instant you energize that solenoid, this logic is functioning. If the cylinder switch is reached, then you start the debounce timer. But in the meantime, down below, it's looking at the extended bit, which won't be, the extended bit won't be on, and this true if off instruction will go false until 200 milliseconds after the switch hits the end of stroke. So we've gone through all this logic. You see the last piece here is the greater than 0. That's just to avoid math problems. That is probably not necessary in this logic. It's just a habit. The multiplier or the multiply instruction calculates the warning interval, and it's based on 75% of whatever you set the preset at, which means if you go in and adjust the preset, the warning will automatically adjust for you. You don't have to change the preset for the fault and the preset for the warning. Okay, now this is the extend logic. Okay, we're going to simplify it. Let's simplify the logic by editing the code to take advantage of something called sequential programming. That's what I call it. I'm not sure what Rockwell calls it in RSLogix5000, but this is where the code steps away from treating this as an electrical circuit. What you're looking at right now, if the TON instruction, the extended bit, the move instruction, another TON, a latch, a multiply, and another latch, if those were electrical loads, and all these things to the left were switches or conditions that were either infinite resistance or a short, meaning open or closed, then this would be an electrical circuit, have an electrical equivalent. With sequential logic, we're going to deviate away, and we're just going to use the instructions in form of a sequence of logic. So let's take the first section there. If the timer is executing and sets the done bit, the extended bit is set. The top rung is conventional and follows the rules of electrical circuit and distribution of loads in parallel, whereas this is sequential logic. So if you look down at the bottom, these two function the same, except for the one on the bottom takes less memory and it executes quicker. So if we read aloud the upper rung, if cycle switch, when you say if cycle switch, that means if it's on, then enable the timer. And if the timer is done, then turn on the extended bit. If the extended bit is on, then one shot the MOV. So you read through that and then read down below there. Look at that rung. If the extended switch is on, then TON. And if done, then extended. And if extended, then one shot the MOV. So it reads the same. The problem with the lower rung is when you look at that electrically, it doesn't make any sense because you're thinking, wait a minute, you can't have a switch, a load, a switch, a load, a switch load, and another load all in series because the voltages will divide up and it won't work properly. Well, this is where we're going to deviate from the older way of writing code to this method. Now, when I first saw this, I thought, oh my goodness, somebody's going to do that. But then, one day it was advantageous for me to do it in this form, to keep it simple, and I've been doing it ever since, and I love it. I mean, once you learn to read ladder logic, you'll read the bottom rung much quicker than you'll read the top one. Because it's obvious that you're not going to move the cylinder extend accumulated value into the tag name extend ET unless all those other conditions have been met. Whereas in the upper one, you actually have to spend a little bit more time looking at it. Okay, here's another piece of that code. And if you read this, if not extended, then enable the timer, and if the done bit, then turn on extend fault. Down below, it's the exact same thing, reads the exact same way. So I'll give you a second to look this over. Reading the bottom rung again, if not extended, then TON. And if the TON is done, then extend fault. Okay, here's our extend logic. And we could probably back all the way up to there. That's what it looked like. And that's what it looks like now. And if you look in there, you'll see in the first section there, if the switch is extended, start the debounce timer, and when it's done, say it's extended, and while you're at it, one shot the MOV to capture the ET. See how much easier that reads? And if it's not extended, then start a timer. If that timer is done, then declare and latch in a fault. Now, the third part of this, the third branch, this doesn't need to be executed because remember, not all the time, not every time, because all it's doing is calculating the warning value. So the multiply could be done only when you're going in and editing presets, because once the extended warning ET has been calculated, you just keep using it. However, the greater than or equal to, which actually sets the latches in the extend warning, that does have to be executed every time this rung executes. So there's the extend logic. There's the retract. Extend, see at the top, cylinder extend solenoid, cylinder extend switch. cylinder retract, solenoid, cylinder retract switch. So we just copy, paste, and then type in new tag names and declare them. Now remember, this isn't your add-on instruction yet. This is just straight code. Now, what else do we have to do? Okay, this is code for diagnostics, but this doesn't actually extend and retract the cylinder. Now, this is more typical what you see. Many programmers like to have a separate file with just the outputs being driven by instructions linked to the actual control logic. So when you look here, you see cylinder 1 manual extend, cylinder 1 auto extend. And then the third branch, you are looking at the actual solenoid output bit and keeping it energized until cylinder 1 is extended. And then you have OK to extend, that's a safety thing, and then you have diagnostic faults. So if you want the fault code to turn off the solenoid, then here's where you put it in. The point is, manual extend and auto extend, those bits are turned on and off by logic somewhere in the control program. But a lot of folks like to have an output file. In other words, a program file or a routine that's called outputs, and that's all that's in is what you see right here. It does actually make troubleshooting a little bit easier. Another thing is the logic will vary with the type of solenoid valve. Double solenoid, single with spring return, detent, return to center, etc. So the logic here that controls the actual solenoid will have to vary with the type of solenoid valve that you have. So then the new instruction, and we add it right with the output simply for troubleshooting purposes. Now, when you look at this add-on instruction, this is an actual add-on instruction that I use in programming. What you see there is what has been declared visible. So like with the timer instructions, the TON, RTO, TOF, you can see the state of the done bit and the enable bit, but you can't actually use those graphics. You can't extend more logic away from those little tails coming out of the instruction. So everything you see here is here for troubleshooting purposes. And by the way, if you look down through there, you've got cylinder extend solenoid, and then you have the actual tag that it references, and it's a local slot 0 output data bit 0. So you have extend solenoid, and then you have extend switch. That's an input. You have the retract solenoid and then the retract switch. So these are actual parameters that are coming in by reference. And then down below you have retract ET. Okay, so you have extend ET up there too. Right below the extended solenoid and extended switch, you have extend ET. Those don't have to be there. You set those visible. So if you're troubleshooting, you can just look there and see what the last elapsed time was for the extend ET. Now, if you wanted to display the actual values for the preset, you can make a lot of things visible in these instructions. And then down below you have, under retract ET, you have reset. That's also an input that comes in by value or by reference. And basically on almost any machine you have a reset button, and that reset button is being accessed here to reset the logic inside of this add-on instruction. So reset is another type of input parameter. Okay, that wraps up just the logic part of our add-on instruction. In the next section, we're going to, we're going to nest add-on instructions. Excuse me, I put something in front of the microphone. So in the next segment of this presentation on add-on instructions, we're going to nest some of these instructions inside of another add-on instruction. Thank you for your patience.